Hello, and welcome to Chapter 21, Alpha Carbon Chemistry, Enols and Enolates. By the end of the chapter, we will be able to draw the mechanism for the acid or base catalyzed tautomerization of an aldehyde or ketone and describe the conditions required for enolate formation. Predict the products obtained from the alkylation process of symmetrical or unsymmetrical ketones and identify the reagents required for a malonic ester synthesis or an acetoacetic ester synthesis. Predict the products of an alpha halogenation of enols and enolates, including an Hell-Wohlhardt-Zelinsky reaction and the haloform reaction. Predict the products of and draw the mechanism for an aldol addition or condensation. Predict the products of and draw the mechanism for a glycine condensation. Predict the products of a conjugate addition reaction and identify the reagents required for a stored enamine synthesis. And lastly, identify two methods for preparing difunctionalized compounds. Let's start with a brief introduction to alpha carbon chemistry. Alpha carbons are the carbons that are positioned one carbon away from the carbonyl bond. Typically, Greek letters are used to describe the proximity of carbon atoms relative to the carbonyl group. So we have the carbonyl group, one position away, you have the alpha position, two positions are beta, and so on. In this chapter, we will focus primarily on reactions that take place around this area where we have the alpha carbon. Alpha protons are the protons attached to an alpha carbon. This is important as you will see later on, and we will see that alpha proton participate in certain reactions. Most reactions covered in this chapter proceed via an enol or enolate intermediate. We have the enol shape with the OH group, and the enolate, which is the anion, a conjugate of that enol. In the presence of acid or base, a ketone or aldehyde exists in equilibrium with an enol. So we have the ketone form, and through tautomerization, we have the enol form. The ketone and enol are tautomers of one another. However, the equilibrium will tend to favor the ketone in most cases. There are some exceptions, we will see them shortly, but typically you can expect the ketone to be much more stable than the enol. Some exceptions, as I mentioned, we have one right here, the 1,3-diketone, in which we have a 10-30% distribution of the diketone, and most of the product in that equilibrium will be in that enol form. That's because the enol of the 1,3-diketone is stabilized by conjugation and intramolecular hydrogen bonding. That allows for a special stability and the difference in the percentage distribution between the two tautomers. Phenol is another example where the enol is vastly favored over the ketone at equilibrium. As you can imagine, the ring that we have here plays a big or significant role in this favoritism. When you have an aromatic system like the one you have here on the right, this is very, very stable. On the left, as you can see, we don't have that aromaticity, so every single molecule that can go and become aromatic, then it will, right? They will. So the equilibrium is vastly favored towards the enol form in this case. Now, it is said that phenol is an enol with aromatic stability. The mechanism for tautomerization will depend on whether you are in an acid medium or an alkaline or basic medium. For acidic conditions, we see here the mechanism for the tautomerization. We have the ketone form, and as you can see, we have an excess of hydronium, which is characteristic of acidic conditions. So you have a protonation step, and when that happens, you have a resonance stabilized cation. So that positive charge is an oxygen that's not very stable. However, you can have a pair of electrons from this double bond migrate, and as a result, the positive charge moves towards the carbon, which makes it a lot more stable than if it stayed in oxygen. When that happens, then we can move on to our next step, which is a deprotonation of that alpha carbon. So that alpha proton goes away, and you have the enol form of this specific ketone under acidic conditions. Under basic conditions, the mechanism is going to look different. So it's rather than a protonation, we don't really have those hydroniums to protonate. Instead, we have hydroxides. So we start off the reaction with a deprotonation instead. So we have an alpha hydrogen that will deprotonate, right? That hydroxyl group will attack. And rather than a cation, you will have an anion, which is resonance stabilized as well. In this case, you have a negative charge on carbon that's not very stable. So what will happen is that that excess pair of, or that pair of electrons will migrate, causing the double bond, one of those pairs of electrons to migrate towards oxygen. The negative charge moves from carbon to oxygen. That makes it much more stable. And that allows for our next step to take place, which is the protonation of that oxygen, allowing you to shift between the ketone and the enol form of that specific molecule. It is safe to assume that some fraction of a ketone aldehyde in solution will exist in enol form, regardless of how that equilibrium is favored. Even if it's just 1 in 1,000, 1 in 10,000, there's going to be some of it. The alpha position of an enol is considered nucleophilic. You have the electron-rich domain, right, as you can see, and that allows for that nucleophilicity. In the presence of a strong base, an enolate will form. So in other words, when you have strong basic conditions or alkaline conditions, then you will see that the protonation takes place, and you will have an enolate which is resonance stabilized, just like we saw in the mechanism a few slides back. So this is actually what you will encounter to a large extent whenever you have a strong base and you have that ketone or ketone aldehyde. The enolate is much more nucleophilic than the enol, as it carries an overall negative charge. The enolate can undergo either carbon or oxygen attack, depending on context, not more than anything else. Enolates generally undergo carbon attack, so that will happen right here. Most of the reactions in this chapter will involve an enolate. So as you can imagine, from everything we've seen so far in this introduction, you have that intermediate, that enolate, that will form, and from there you carry out the rest of your reaction. You can expect that this will be a big part of many, if not all, of the reactions that we'll see throughout this chapter. Now let's talk a little bit about alpha protons. Alpha protons are the only acidic protons on an aldehyde or ketone that can be removed to form an enolate. The beta or gamma protons are not acidic. The protonation will not yield a resonance stabilized intermediate. So that means that when you're in the alpha position, so right here, these protons right here are the ones that we're talking about when we talk about forming that enolate. This one, that's not an alpha proton, right? Because you need a carbon to be in the alpha position and then those protons. So these are the only ones that qualify in this case. The pK value of alpha protons must be considered when choosing an appropriate solvent or an appropriate base to form an enolate. pK values, as you can expect, ridiculously high, from 15, 16, all the way to 19, 20, etc. When the pK values of the base and the enolate are similar, both products and reactants are present in significant amounts. We have here an example of two pK values. Here, for instance, we have a 19, here we have a 16. The numbers seem kind of close, but keep in mind that this is a logarithmic scale, so a difference of 3 means that you have a difference or a factor of 1,000, by 3 orders of magnitude. So that's fairly large. So the equilibrium will tend to favor the one with the highest pK value. When the alkoxide is used, the enolate can react with the ketone. Now, to irreversibly and completely form an enolate, a stronger base must be used, like sodium hydrate, for example, where you have that hydrate come in and actually generate hydrogen as a product. That's how you get that enolate to form in an irreversible fashion. LDA, or lithium diisopropylamide, is a strong base commonly used to form enolates irreversibly. It is made by treating diisopropylamine with N-butyl lithium. So this is the structure, LDA. I would advise that you sort of familiarize yourself with it. We will see this fairly often throughout the rest of the chapter, or this specific structure, what I mean. When LDA is used to form an enolate, the amount of ketone present at equilibrium is negligible. LDA features two bulky isopropyl groups, we see them right here and right here, which allows it to be a strong base, but not a good nucleophile. So basically, not being a good nucleophile allows you to pull the best from both worlds, right? You have that deprotonation step, and you don't really need to have an equilibrium. So it goes irreversibly towards your enolate form. When protons are alpha 2 carbonyl groups, they are much more acidic. The increased acidity is due to increased stability of the resulting enolate. So you have that resonance stability, and as you know, whenever you have a higher level of conjugation, you have a higher level of possible structures, right, that contribute to that hybrid of resonance, then your overall structure becomes much more stable. That's what this means. 1,3-dicarbonyls are acidic enough to be irreversibly deprotonated by an alkoxide. So here, for example, we have an alkoxide. It deprotonates that 1,3-dicarbonyl and it generates that enolate. And as you can see, the arrow is going in one direction, so that indicates that you don't have an equilibrium. This is an irreversible process. In this case, there would be no need to use sodium hydrate or LDA to form the enolate of a 1,3-dicarbonyl. It would be overkill, and if you're in a lab, neither sodium hydrate or LDA are things that you really want to use if you don't have to, so you probably won't. It is important to know what base to use to generate an enolate, depending on the carbonyl compound and the desired result. Do you want a reversible process or an irreversible process? And we have both scenarios here. When you have your carbonyl, you want to form your enolate, you treat it with a strong base. This becomes reversible. When you treat it with sodium hydrate or LDA, you still get that enolate, but it becomes irreversible. If you have a 1,3-dicarbonyl, then you don't really need LDA. You're gonna get a irreversible or nearly irreversible process. The alpha position can be alkylated when an enolate is treated with an alkene halide. So in this case, we would use LDA, for instance, followed by an alkyl halide, whatever we need at that specific place, right? The R group will be added to the alpha position. The enolate attacks the alkyl halide via SN2 reaction. So that means we're dealing with a one-step process here. Regioselectivity is an issue with unsymmetrical ketones. In this case, two different enolates can form. As you can see, we have the double bond forming here, and it depends on relative stability of those products. So for example, if you look at the one on the left, this is what we call the thermodynamic enolate. Thermodynamic refers to the overall stability, the overall energy of the system. When you have the thermodynamic product, that usually refers to the more stable product. Now, usually when you have the thermodynamic product, and you're dealing with that, that means that you're probably also talking about the kinetic product. The kinetic product is the one that is going to form the fastest. So here, this position, you have a little bit more steric hindrance than in this position on the right. So this is bound to be formed a lot faster. However, it is less stable. So you have that competition between the thermodynamic enolate and the kinetic enolate. And it all comes down to the overall energy. You can see the kinetic and thermodynamic pathways. Kinetic, if formed faster, you have a smaller activation energy. So you're going to get a little bit of that kinetic. You're also going to get a little bit of that thermodynamic enolate. Now, when we're dealing with irreversible conditions, the kinetic enolate is the one that tends to be favored. So for that, you can use LDA, we don't even need to go to high temperatures. So LDA, low temperatures, you get the kinetic enolate. And when you have reversible conditions, then the thermodynamic enolate is favored. In which case we can achieve that by using sodium hydrate. We have the two routes here depending on which product you want. Under acidic conditions, ketones and aldehydes undergo alpha halogenation. So those alpha protons that you have, one of them is going to be substituted for a halogen. In this case, we're dealing with bromine. It works with pretty much every halogen except for fluorine. Acidic conditions means that an enol is the reactive intermediate. And with dealing with acidic conditions, that means that you can already tell what that mechanism is going to look like. Let's check it out. Part 1 will be that enol formation. We already saw this at the beginning of the chapter. We have a protonation followed by a resonance stability step and a deprotonation of that alpha hydrogen. Once we have that, then we proceed to a nucleophilic attack and lastly a deprotonation step to generate your final product. Now when you have an unsymmetrical ketone, then halogenation is going to happen a lot faster at the more substituted carbon. So what that means is that, just like we saw before, you're going to have two potential products because you have two sites where you have alpha carbons and alpha hydrogens. So you're going to have a halogenation here and a halogenation here. The more substituted carbon will allow for that product to be in the majority. So this is the major product, and the minor product will be the one with the least substituted carbon. The major product resolves for the more stable, as we mentioned, tri-substituted versus di-substituted. Alpha halogenation provides a two-step synthesis for the formation of an alpha-beta unsaturated ketone. In this case, we're adding, right, double bond here, and for that, first we do acid conditions, halogenation, and then we add pyridine. Other bases can be used for the elimination process, such as terbutylate or lithium carbonate, just to give you a few examples. Now let's talk a little bit about the HVZ, or the Hell-Borhard-Zelinsky reaction, which brominates the alpha carbon of a carboxylic acid. So you look at a carboxylic acid, look for the alpha position, and here's where you're going to get that bromination. The mechanism is believed to be the following sequence. Now these reactions are fairly fast, so some of those intermediates are very difficult to catch and to sort of figure out. So we do have some models, but that's as far as we have gotten. Here we have PBr3 reacting with the carboxylic acid at the alpha position. We have that keto-enol tautomerization followed by a halogenation, and then you have the substitution of that bromide for that hydroxyl, so you get that carboxylic acid back. Alpha halogenation can also be achieved under basic conditions, as you can imagine. Under basic conditions, the enolate is going to be the reactive intermediate. As you know, we have a deprotonation step that sort of kicks off everything. Once we do that, we have our intermediate, we have the enolate forming, and from there you have the attack that will allow for the halogenation. Under basic conditions, methyl ketones are converted to carboxylic acids using excess halogen and hydroxide. This is what we call the haloform reaction. So here, for example, we have, this is a methyl ketone, right? You have a methyl group right here. So you have a strong base, hydroxyl, followed by the halogen. And as a second step, we add hydronium, right? We add acidic conditions. So as a first step, you add that bromine, we'll be substituting those protons. This is only an excess now of the halogen because you're gonna need at least 3. Once you do that, then the acid will allow for this to sort of break off and give you a hydroxyl group, so carboxylic acid. So let's talk a little bit about that mechanism. After all 3 alpha protons are replaced, the CBr3 or the carbon tribromide acts as a good leaving group, and acyl substitution happens. The resulting carboxylic acid is deprotonated under basic conditions, which forces the reaction towards completion. Now let's talk a little bit about aldol reactions. Let's think back and recall that when an aldehyde is treated with hydroxide or an alkoxide, an equilibrium forms where significant amounts of both enolate and aldehyde are present. If the enolate attacks the aldehyde, then an aldol addition reaction occurs. So here, for example, we have an aldehyde, strong base, under water conditions or aqueous conditions, you get the beta hydroxyaldehyde. You have an alpha position right here, that's the one we're looking at. The product features both aldehyde and alcohol groups. Note the location right here in the beta position of that hydroxyl group on the beta carbon. Under basic conditions, the enolate is going to be the reactive intermediate. The mechanism is very similar to what we've seen so far. So you have a deprotonation step. You have that enolate intermediate, and that's what allows for that nucleophilic attack to happen. So you attack the carbonyl with that alpha carbon, and then you get a protonation. The aldol addition is considered an equilibrium process. When we're talking about simple aldehydes, the product tends to be favored. However, when we're dealing with ketones, in most cases, the aldol product is not favored. When we look at the reverse process, this is what we call a retro-aldol reaction. The mechanism is simply the reverse of the aldol addition. So if you know one, just flip all the arrows and you have the other one. When an aldol product is heated under acidic or basic conditions, an alpha-beta unsaturated carbonyl forms. This is what we call an aldol condensation. So you have the alpha-beta position. Here you have an unsaturated, so you have a double bond, and that's basically what happens. Aldol condensation will happen when an aldol addition is performed at high temperatures. So we have, for instance, here the aldol addition, right, in lower temperature and other conditions. If you heat it up, you instead get the aldol condensation. Now let's take a look at that mechanism. For the aldol addition, it's going to be the first part of this process. We start off with a deprotonation of that alpha hydrogen, followed by an electron pair migration or the formation of the enolate. Now that enolate will serve as a nucleophile and attack an aldehyde. So you need two equivalents, as you can see, for this reaction to happen. Stoichiometric, it's going to be at least 2 to 1. Now the resulting alkoxide, right, the negative charge, is then protonated. So we're assuming aqueous conditions. Now once that happens, we move to the second part of the process, which is the elimination of water. We start with a deprotonation of that hydroxide, and that will generate an unsaturated system or a double bond, which will migrate or move in the next step when you have the loss of the leaving group, that OH, and you have the alpha beta unsaturation. So carbonyl, alpha beta, that's where we are. Now when we have two different aldehydes or ketones, they can react in what we call a crossed aldol reaction or a mixed aldol reaction. Two different types of aldehydes will yield up to 4 different aldol products, as you can see here. Crossed or mixed aldol reactions are only practical if the number of products can be minimized. Right? If you're trying to make just the one product, and this is horrible because you can end up with up to 4 different products, and you will then need to find out how to purify, how to isolate, your yields go down. So it's not really something that the scientists look forward to. One of the substrates is relatively unhindered and without alpha protons in this scenario. So this right here. In this case, because it doesn't have any alpha protons, that this can't really be attacked right in the alpha position, that means that the aldol reaction will only happen here. This is possible when only one compound can form an enolate, and the other compound reacts with the enolate faster. So when that happens, you only get the one product instead of a bunch of them. In this case, we're using LDA as a base. That's what we call a directed aldol addition. So we sort of force the issue. And when that happens, then you form the enolate only here. And from there, you can then have your alpha beta reaction. One compound is completely converted to enolate with LDA. Remember that this is irreversible. The other carbonyl compound is then slowly added to the enolate. So all of these are things that you can control on an experimental setup, right? So you basically you force this to happen first, and then once it happens, then the same container, you add the other carbonyl compound. Now, another type of reaction that we may see are what we call intramolecular aldol reactions. They tend to form cyclic compounds. One group forms an enolate that attacks the other group, and usually with decent yields, you get 5 to 6 member rings, depending on the specific dicarbonyl that you're using. Esters also undergo reversible condensation reactions, and those are the ones that we call glycan condensation. This is simply a nucleophilic acyl substitution reaction. So the nucleophile will be the enolate of an ester, and the electrophile will be the ester itself. Let's take a look at that mechanism. The mechanism will start off with a deprotonation, that alpha hydrogen, followed by a nucleophilic attack. In this case, the enolate serves as a nucleophile and attacks an ester, forming a charged tetrahedral intermediate. Now, once that happens, you will have a loss of the leaving group right here, or the collapse of that intermediate. This will lead to the ejection, right, or the loss of an alkoxide ion and the reformation of the carbonyl group right here. Lastly, we have a deprotonation step in that alpha position. You look at proton, and then you form the highly stabilized enolate. The last step drives the reaction to completion. Acidic workup is necessary to obtain the neutral product, instead of the one that we have here with a negative charge. There are, as you can imagine, some limitations to the glycan condensation. First, the starting ester must have 2 alpha protons, because removal of the second proton by the alkoxide ion is what drives the equilibrium forward. Second, the hydroxide cannot be used as the base to promote glycan condensation. Otherwise, ester hydrolysis will likely take its place. Third, an alkoxide that matches that OR group in the ester is needed. Otherwise, transesterification is what will end up happening. One ester, here for instance, we have a few examples. One ester has no alpha protons. That sort of forces the glycan condensation to take this very specific form. We perform direct glycan condensation with LDA as the base. So these are a few ways in which we can end up with the desired product. Now, when we have intramolecular glycan condensations, which can happen, they can be achieved, and they're called the Dykman cyclization. Like with all the reactions, Dykman cyclization prefers the formation of 5 or 6 member rings. Now, going back to that alpha-beta unsaturated carbonyl, they're made via aldol condensation, as you can see here. Alpha-beta unsaturated carbonyls, they have 3 resonance contributors. That's what makes them so stable. You can see the resonance structures. And as you know, the more resonance structures you have that are relatively stable, then the more stable the overall product becomes. Alpha beta unsaturated carbonyls have 3 resonance contributors, as we just mentioned right here. The beta carbonyl and the carbonyl carbon are, as a consequence, electrophilic. Either carbon can be attacked depending on what nucleophile we're using. So you can be attacked here, or you can be attacked actually here or here. Grignard reagents generally attack the carbonyl position, which is what we call a 1,2 addition. However, we can use Gilman reagents to attack the beta position. This is called a 1,4 addition or a conjugate addition. This is great for us because now, depending on where we want that addition of that R group, then we can choose between the Grignard and the Gilman reagent. Now for the conjugate addition, this is the general mechanism. You have the nucleophilic attack, followed by the migration of that double bond of that pair of electrons, right, the movement of electrons to stabilize your entire system. The consequence of that movement is the formation of the enolate. After you have that nucleophilic attack, you have a protonation step, and you get the enol. The enol will then tautomerize to the aldehyde or the ketone, depending on specific context. Stronger nucleophiles will lean or will tend towards 1,2 addition, and less reactive nucleophiles will actually tend to do conjugate addition. Typical enolates often will give you a mixture of 1,2, 1,4 addition products. Stabilized enolates, on the other hand, will lean exclusively towards 1,4 addition. So this is a scenario in which you can have that addition, right? You have a strong base, you have the group that you're adding, and then the acidic workup. The conjugate 1,4 addition is called a Michael reaction. Michael will be the donor, which is a nucleophile that undergoes a conjugate addition, and the Michael acceptor will be the electrophile. The following, the ones that we have here in the table 21.3, they give exclusively 1,4 addition with an unsaturated carbonyl. This is perfect because now, based on the type of product that we're looking to form, we can then just pick from the table which a donor or acceptor will be working with. Because singly stabilized enolates do not give high-yielding Michael additions, Hilbert-Stork develop a synthesis using an enamine intermediate. Now, looking back at how enamine is made, right, we have that secondary amine with an acidic conditions, you get that enamine formed. Enamines behave just like the enolate, and they are nucleophiles, so slightly a little bit less electronegative, but otherwise basically the same. However, because it's less electronegative, the enamine is also less nucleophilic, and it is considered a Michael donor. After conjugate addition, aqueous acid converts both groups into carbonyl groups. So you have, in this case, you have the Michael donor, which you see the attack here, and then the migration of the lone pair of electrons from nitrogen to stabilize the system. Iminium, and then your enolate. After this, you want to be able to remove the negative charge, so for that you add an excess of protons. Now this is known as the three-part process, Stork-enamine synthesis. First step, the formation of the enamine, followed by a Michael addition, and concluded with a hydrolysis. Now the last reaction will be the Robinson annulation, which is a two-step process for forming a ring, specifically Michael addition, followed by intramolecular aldol condensation, as you can see here.